this one. So the dot product is basically when you multiply two vectors together. It is a scalar. So what that means is that you're actually going to multiply it together and then you're adding all the components. Notice how there isn't like an x hat vector or y hat vector here. That's because we're multiplying the magnitudes, and that's going to be our answer. So I'll show you kind of two different ways that you would approach this depending on how the vector you were given looked. So if I have a, right, is equal to 1x hat plus 1y hat plus 1z hat, and then I have b is equal to 1x hat plus 2y hat plus 3z hat. If I do the dot product, and I'm given these vectors where I have the Cartesian coordinates instead of polar, or instead of a magnitude and an angle, what I would do is I actually would multiply each piece together. So I would basically have like 1 times 1 plus 1 times 2 plus 1 times 3. Okay? So that would look like, oops, and I'm going to add them together. So I have a dot b is equal to 1 times 1, okay, plus 1 times 2 plus 1 times 3, okay? And in this case, it's going to equal 1 plus 2 plus 3, right? So our answer is going to be 6, okay? That's the results for a dot b. Okay, so what if I'm given two vectors? I have a vector here, and it's equal to 3. I have a vector here, and it's equal to 6, the length of it. I don't really know the direction. This is just my magnitude. So I have the magnitude of just kind of the a side here. Oops, my notation is a little sloppy, I'm sorry. So I have the magnitude of the a side is equal to 3. And then let's say b, my magnitude of b is equal to 6, okay? And I know that the angle between them is 30 degrees. Well, I can still use the dot product. This is just a different formula for the dot product, okay? So this is also useful if you want to find the angle between two vectors, because if you remember the magnitude formula, like if I just wanted to find the magnitude of a, right, and it would be like 1 squared plus 1 squared plus 1 squared, so the square root of all of the components squared. So I could find the magnitude of a, and then I could also find the magnitude of b, right, and I could use that to solve for my angle between two vectors. So that might be a common application of this. So 1 squared plus 2 squared plus 3 squared. So for example, so these are the first two vectors that we did. So in this problem, actually let me use the same. So let's say square root of, what, 3 squared, so square root of 3. This would be equal to 9 plus 4 plus 1, so square root of 14. Okay. So in this case, so let's use the same numbers here. A is equal to the square root of 3, and let's say b is equal to the square root of 14. And let's say we don't know the angle. Let's find the angle between these two vectors, okay? Well, to find the angle between those two vectors, I would take the magnitude of both. So it is square root of 3, square root of 4, and then cosine of the angle. And then we have our result for the dot product, right? Because the dot product is on this side. So let's say it's equal to 6. So 6 divided by square root of 3 times square root of 4 equals cosine of theta, and theta would be equal to the inverse cosine of 6 over square root of 3 times square root of 4. Okay, so you could use this. There are better ways to, do this. I would recommend using like a trig triangle. But when you are dealing with three-dimensional vectors, you can't really approach it in the same way. It's a little trickier, so this actually does help quite a bit, I think. So yeah, you could also similarly, like say I have, two sides. I have, it's in this case, let's call this C is equal to 4 and D is equal to 3. And then I have an angle of 30 degrees and I want to know my dot product. I basically could just do, so I could do C, dot B for the vector is equal to CB, the magnitudes, so the lengths of the sides, cosine of 30 degrees, right? Because that's this equation right up here. This equation, so cosine of 30 degrees. Because that's the angle between them, the smaller angle between them. And I have C dot B is equal to, what were the magnitudes here? I had 4 times 3 cosine of 30 degrees. Okay. and that would be my dot product. You can simplify that a little bit more. I'm just trying to blow through these here. Okay, so basic properties of the dot product. If you have a vector dotted with itself, so these are bold. This is basically meant to imply that these are vectors. I'll put the little, put these on top of them. The double line that you see here is the same as that single line. It's just a different notation to write it that way for magnitude, but it just means magnitude. So magnitude. So what this is saying is that if I dot two vectors together, it's going to be equal to the magnitude squared. So like say my magnitude of my vector A is equal to 3, and it's the exact same vector. I'm doing A dot A, like a vector dotted with itself. The magnitude is going to be equal to the result is going to be equal to the magnitude of the vector squared. So, so the magnitude of A squared. So like in this case, say I found, say my magnitude is equal to the square root of 3 here. So that would mean that A dot A, right, is equal to the square root of 3 squared. So A dot A would be equal to 3. Okay. Then for this guy, basically we're pointing out that the properties are commutative here. So like you can do it any direction. V dot W is equal to W dot V. The distributive property is also true for this. This one is a little more confusing, but it's basically just like a constant. Lambda could be any number. So say it's like 4. Basically it's saying like 4 V dot W would be equal to 4 times V dot W. So it distributes, which is equal to V dot 4W. Okay, so the distributive property is true here. Again, they write them in bold to represent that they're vectors. I will put the symbols on there because I think it's a little easier for you guys to read in the notes, but that's what that means. Okay, so we're going to move on to the cross product. So we haven't covered this yet. Essentially, the cross product is probably not something you're going to use very much in this class. You might use it for torque or something like that. It's basically something that follows what's known as a right-hand rule. So, for example, I think I have a really nice drawing over here. So if I put my pinky finger along A, right, and then I sweep my hand, as you see in the drawing here, along B, where my thumb is pointing, that's where the direction of my cross product is going to be. Because the cross product is not a scalar, the end result of the cross product is going to have a vector direction, and the vector direction is going to be normal to, or perpendicular to, the plane that A and B are on. Okay? So, alright, so just like say for example I needed to do a vector cross product here. I could do kind of the same rule. So remember we explained that we could do AB sine of theta to find our cross product. So if I had two vectors, in this case like A and B, and I wanted to find A cross B, my resulting vector would be like in this direction, BC. So say B is in the x direction and A is in the y direction, okay, and it's just flat on a plane here. If I do y, or x cross y, this would be in the positive z direction. So y positive z, right, coming towards us? Yeah, positive z direction. I think mine might be flipped around a little bit. Let's go down to the actual drawing so I make sure that I'm not telling you something that's wrong here. Here we go, x, y, and z. Yeah, so x cross y. So if I think about, so imagine right now with me, pinky along x, along this direction, and we're going to sweep to y, and then your thumb is going to point up. So that would be positive z. Okay? So that's how that works. When people say the right-hand rule for the cross product, that's exactly what that means. Okay? So, yeah. If you have a three-dimensional vector, or a two-dimensional vector, you can use this general equation to find the cross product. So say I have A is equal to 1x hat is 2y hat plus 3z hat, and B is equal to 2x hat plus 2y hat plus 3z hat. What I would be able to do here, just look at all of these components. So I have AY, BZ. What is AY? So I have 2 maybe I should make all the numbers different, just to make it a little more less confusing. I'll do 1/2 x hat plus 1/3 y hat plus 1/4 z hat. And I'm just going to write it out instead of solve it to kind of show you what it would be. So your cross product might have more than one vector direction, because if you think about it, if your vectors don't line up exactly, you know, on these unit vectors, and say I have a vector that is some portion of, you know, x and y, when I take a cross product of these two vectors and I get a resulting vector that's pointing up, it's going to kind of be like skew to one of these axes. If that doesn't make sense to you, just go ahead and try to like look at two vectors that aren't aligned with x and y, or aren't parallel to it, and see what your result is going to be. So like we're going to do here. So I have, right, so this is AY, right, this is AX, this is AZ. Essentially I would just plug these in, BX, BY, BZ. I would plug these into this equation over here. This result is linear algebra. I have some more, like the solution to basically doing a determinant for linear algebra. You don't need to know what that is. I doubt it will be important to you in this class. If you take more math, it will be. But I included it in a note sheet. I won't go too hard into that here. I think that might be a waste of your time. Okay, C equals A cross B. Although I do think linear algebra is really important and you all should take it, but as future medical students, maybe some of you might not. So A, Y, B, Z. So for example here, 2 times 1/4, right? Minus this AZ. AZ is equal to 3 times BY, 1/3. Okay, and that's in the x hat, right? Plus AZ times BX, 3 times 1/2, right? Minus AX times BZ, minus 1 times 1/4, y hat, okay, plus 1 z hat, AX BY, so AX BY, 1 times 1/3. I'm afraid I'm going to make a mistake here just because this is like a little long and tedious. And then AY BX, so 2 times 1/2 z. Okay, so essentially I would simplify here, and my result for C would be some value that's like CX in the x hat plus CY in the y hat plus CZ in the z hat, and that would be my cross product. I am also able to use this to solve for my cross product, but you need to be aware of your vector direction. So the way that they wrote this here is they wrote that the magnitude of the cross product is equal to this. Yeah, so you could basically use this expression to find the magnitude. It would not be able to give you the direction. So, okay, properties of the cross product. If you switch the order, it becomes negative. If you switch the order you do it, it becomes negative. It is distributive. You can distribute the cross product. And then multiplying by a constant is also okay. All right, so if I have like lambda is equal to 4 or something, or 3, just any constant number. Okay, so this is a drawing we saw before, kind of with a little bit about where the cross product ends up. So if I do A cross B, so sweep my fingers here, thumb is pointing up in this direction, as we kind of see over there. So it's just a visual to kind of help you guys understand it. Again, this is probably more than you need, but I just want to do a soft intro here. One important thing that's actually really useful about doing the cross or the dot product is you can use it to tell if two vectors are perpendicular or if they are parallel. If the dot product is equal to 0, that means that the two vectors are perpendicular. Essentially, if you plug in cosine of 90 degrees, you can see that this is the case. The dot product is also telling us like how much of one vector is in a shared direction with another vector. If they're perpendicular, they don't share any direction. Okay? Are two vectors parallel? So for this one, if there's no angle between them, if you think about it this way, so sine of these angles for the cross product this is the angle between them, so this would be the magnitude of the cross product, right? So the magnitude of this, magnitude. So if the magnitude of it equals 0, then there is no angle between them. So you just end up with this AB dot 0, because the angle between them would be 0, so it would set it to 0. So you can tell vectors are parallel by using the cross product. Okay. This is just a little bit on Cartesian coordinates. These little a's mean the same as x hat dot x hat or y hat dot y hat. It's just a different notation. Don't worry about this page really. I just really wanted to point out that essentially if you dot these like unit directional vectors with themselves, if I have x hat dot x hat or y hat dot y hat, it's equal to 1. Okay? Or if I do a cross product, if I have like x cross y, it's going to give me z, so this would be like x hat cross y hat equals z hat. But then if I switch the directions, if I have y hat cross x hat, it's going to be equal to negative z hat. And I want you to try to like visualize it and see why that would be. So like if you take y, put your hand like upside down so your thumb is pointing down and you're sweeping y to x, that thumb is how you get the direction for the cross product, okay? So this thumb over here. So basically it's like you're turning your hand upside down so that your thumb is pointing the other way. And because of that, you can tell that the direction is going to be negative. Okay, last thing I want to point out is if you're just given 2 random points, how to find a vector from those points. You basically, the subtraction is kind of opposite of what you would think. So if I'm given an origin point, so in this case like O is equal to 0, 0, 0, and a point in space is equal to negative 0.2, so I have it written kind of out here. So just this point in space here. The way that I would find the vector from 0 to p, so like if I was drawing it and I just had a 3-dimensional coordinate system and imagine that, I don't think this will line up because this is negative 0, 2.3. So if I just had, for example, some theoretical point, and I wanted to find the vector to the point, I would call the vector OP, and the way I would find it is I would take the point and I would subtract where it's coming from, and then that would be my vector. So I kind of have some work out here. So you can see I have p minus 0, 0 minus 0. A lot of these things, a lot of the things in this class that you're dealing with, your vector is going to be coming from the origin. So like all of your vectors are going to start with the tail at 0, 0, 0. But if you end up with something different where, like you have a vector and the tail of that vector is not at the origin, not at origin, this might be useful to you to just find the vector. So it's the destination point minus the source point. Okay, so like where it's going, where it ends up, minus where it came from. Okay? So that's all I have for vectors. Sorry, this was a little bit long. Hopefully this overview helped clear up some points that you might feel a little bit fuzzy with. The cross product stuff will not be important yet. I just kind of wanted to intro it a little bit, and I will leave this cheat sheet with you in case things come up in lecture or in your homework where this ends up being useful to you.